far, when we're talking about the speed of a reaction, the only way to determine the rate law is by looking at experimental data, because I told you you cannot look at the stoichiometry of a reaction to determine the rate law. Well, what we're going to do now is actually look in detail at what's behind one single reaction and realize that we actually can determine a rate law if we look into the details of a specific reaction. So the first thing we need to talk about is a reaction mechanism. So the reaction mechanism is the detailed steps that occur as the reactants are turned into products. So when you see one single reaction with reactants and products, that's not all that's going on. There's a lot of behind the scenes action that's happening. You rarely will see reactants and products, and that's the only thing that was involved in the reaction. Instead, reactants will be transformed into intermediates, which are then eventually going to be turned back into products. So there are a number of steps that occur. Elementary reactions are each single step in a reaction mechanism. So if you have 3 different elementary reactions, those can add up to your final reaction, and we'll see that in detail in just a couple of seconds. The last term that we need to go over is molecularity. Now, molecularity is the number of molecules that participate as reactants in an elementary reaction. So let's look at this example. You have unimolecular, meaning one molecule. So if you look here, the only way to have a unimolecular elementary reaction is if you just have one single reactant. It can be bimolecular, meaning you have 2 molecules, 2 of the same molecule, or it can be bimolecular if you have 2 different molecules. It can be termolecular if you have 3 of the same molecule. It can be termolecular if you have 2 of one molecule and 1 of a different one, or you can have 3 different molecules and it still be termolecular, meaning 3. You don't go above ter. So let's look at this mechanism. Now, if you notice, you have 2 elementary reactions. Okay? The first step, that first elementary reaction, is bimolecular because you have 2 molecules there, and the second step is also bimolecular. And so let's actually look at the reaction that these 2 steps add up to. So each of these elementary steps will add together to form your overall reaction. Notice I have 2 NO2s on my reactant side from step 1 and 1 NO2 on my product side. And so if I cancel things out, that ends up giving me just 1 NO2, 1 nitrogen dioxide on my reactant side. Notice that my nitrogen trioxide, my NO3s, I've got 1 on the reactant side, 1 on the product side from step 1. So those are going to cancel. So I eliminate those. Carbon monoxide, there's only 1 on the reactant side, so I'm going to leave that. And then I have 1 nitrogen monoxide, which I'm going to leave, and then 1 carbon dioxide. So my overall reaction is going to be nitrogen dioxide reacts with carbon monoxide to produce nitrogen monoxide and carbon dioxide. So that's my overall reaction. Now, if you looked at that, you wouldn't have realized that there are 2 elementary steps that are needed in order to form that overall reaction. So that's what we're going to be dealing with in this section. So what species appears in the mechanism, but not in the overall reaction? And how are these different from the transition states? Well, the species that appear in the mechanism, but not in the overall reaction, as you can see from this example, one example would be nitrogen trioxide, because it's not in the reactants, it's not in the products, but it shows up in the mechanism. And that is called your intermediate. Now, your intermediate is different from your transition state. Notice your transition state exists at the peak of your potential energy curve. And your intermediate is different from your transition state because an intermediate is stable and you therefore can actually identify it and isolate it, while transition states are not stable and you are unable to isolate them. So the rate law of an elementary reaction is simply based on its molecularity, and the rate law for an elementary reaction can be written directly from your reaction. Coefficients are going to be used as exponents in your rate law. So in contrast with an overall reaction, you can actually take an elementary step and use its stoichiometry in order to determine the rate law. For the overall reaction, you can't do it, and you have to do it experimentally like we did in previous lessons. So let's look at an example. Here I've got step 1 and I've got step 2. The overall reaction, I need to add these 2 elementary steps together. Notice oxygens, the O's are going to cancel each other out. And so what I'm going to be left with is 2 N2Os, 2 dinitrogen monoxides, and 2 nitrogen gases, and 1 oxygen. And so the intermediate is the species that it does not show up in the reactants or the products, so that would just be oxygen. The molecularity is going to be unimolecular for step 1, bimolecular for step 2. And then finally, the rate law, I'm just going to use the stoichiometry. So for step 1, the rate equals my rate constant K times the concentration of N2O. For step 2, my rate would be my rate constant times the concentration of dinitrogen monoxide times the concentration of oxygen. Now, the fact that oxygen is an intermediate is going to become an issue, and we'll look at that in the next lesson. So how exactly do we determine the rate law of an overall reaction? Because in the previous slide, I had 2 different rate laws, so how do I know which one it's going to be? Well, in this lesson, I'm just going to work with mechanisms with the slow initial step. And then in the next lesson, we'll look at the case when your slow step is not your initial step. So if you look at this example, your slow step is your first step. And so what we're going to do is we're going to assume, since the first step is your slow step, that is going to determine the rate of your reaction. And therefore, we can simply use the slow step for your rate law. So the equation for your overall reaction, we're just going to sum these reactions together. All right, and so we already did this in the previous problem, so I'm just going to write your answer right there. And so what I'm going to do for the rate law, all I have to do is use the slow step, because that determines my rate, to determine the rate law. Now, keep in mind, this is an elementary step now, so I can just use the stoichiometry to determine my rate law. So all I'm going to do is say rate equals my rate constant, which is K, times the concentration of N2O, and that's my rate law. So it's really convenient as soon as it's broken down into your elementary steps, because then I can use the stoichiometry. So these problems are not hard at all. They're different from when I used experimental data, simply because once you're able to break down your reaction into its elementary steps, then you can use stoichiometry and the molecularity in order to write your rate law very easily. Now, the last thing that I'm going to go over in this lesson is catalysts. Now, a catalyst is a substance that changes the speed of a chemical reaction without undergoing a permanent chemical change itself. And the way that they do that, catalysts lower the activation energy for a reaction by providing a different mechanism for the reaction. So as you can see in this graph, the red represents an uncatalyzed reaction. And so what a catalyst does is it provides another way for a reaction to occur. And ultimately, by providing another mechanism, it lowers the activation energy. By lowering the activation energy, which is ultimately what dictates the speed of a reaction, it actually speeds up a reaction. And so in order to identify a catalyst, you simply have to keep in mind that it's going to exist as a reactant, and it's going to exist as a product as well.